As you can see here in the second part of the lecture, that is digital filter stability. So first of all we have to discuss about what for IIR filter what will be the GZ. In the GZ section here you can see that there are numerator section and denominator section in both parts, and both are the power series of AIZ divided by Z minus alpha I. And for stability purpose we have to note that yk is equal to xk minus b yk minus 1, that's minus b to the power k. Yz is equal to xz minus b z inverse minus 1 yz, and yz by xz is equal to 1 by 1 plus g b z inverse, and also z divided by z plus b. That's the stability factor. Now you can see the digital filters, thus there is a pole at z equal to minus a in the previous section. If its magnitude is more than 1, then the impulse response increases without bound. If its magnitude is less than 1, decreases exponentially to 0. And frequency response set xk is equal to e to the power j omega k capital T, and yk is equal to a omega e to the power j omega k t. So that you can write the equation like that, and after that you get this type of value with numerator and denominator sections. So compare with transfer function z to the power minus 1 exponential minus z omega t. So there is a 2D z transform. As you can see that is 2D means that two functions are there, z1 and z2. So that is a 2D z transform equation, and there is an example solving these equations in the 2D form. And 2D digital filters are like that, that is yk1 k2. Simply in the previous sections they will be additive, that is the additive section, that is the scaling section, and the delay sections are there. And if it's IIR filter, so that will have to be b and y equation, and b coefficients are there. Thus we can have FIR 2D filters and IIR 2D filters. And as you can see here, the transfer function looks like that, z1 comma z2, and the a and z1 will be in the numerator section, and b and z1 with plus 1 will be the denominator section. For convolution set we can get this type of equations like that. So that is the 2D filter with typical filtering sections. As you can see, there are some matrices of A02, A01, A00, A12, A11, A10, A22, A21 and A20, as like as the B02 and others. So both are additive, both matrices are additive here. So typically there is N1 is equal to N2, M1 is equal to M2, IIR is equal to 2 arrangement. So this filtering is set by like that. The denominator sections and numerator sections has been put onto the pole 0 format with a type of matrix format. And here you can see that in filtering section, if there is a problem, the dot function, the dot is there, as you can see here. So separable filters, 2D digital filters, as you can see, G is equal to Z1 comma Z2, G1 Z1, G2 Z2. Non-separable filters, it will be G Z1 comma Z2 is not expressible as a product of separate and independent factors. So what are the ideal filters? The ideal filters are like that: the band pass, the band stop, and the impulse functions on the both sides of the band pass and band stop. Here you can see that there is the ideal filter occasions. And last but not the least, that is the ideal filter. What can you say? Pole zero graph? Not, it's a pole zero graph. That is the frequency domain section from minus pi to pi. That will be the response, the frequency response of ideal filter. Thank you very much for being with me.